let's go ahead and get going, folks. This is the last session, and as with everything virtual and hybrid, something's going to change, and it's going to change in this session. Our first two presenters are not going to be joining us, so we're going to go straight into our third presentation. The good news is that we're going to get out of here a little bit earlier. I'm also going to take maybe 10 or 15 minutes, and I'd like to show you all something that I've been working on for a while that I think is a great feedstock in the waste conversion area. You know, we're starting the Agricultural Plastic Recycling Conference right after this, and I want to share with you a waste stream that is extremely problematic, but I think offers a lot of opportunity down the road. So let's go ahead and kick this session off. Our first presenter is J.L. Kindler. Kindler, yes, sir, with he's CEO of Waste2H, which is, I'm assuming, hydrogen. And JL is going to be talking about how waste-to-hydrogen technology is scaling to supply fuel cell vehicles, power generation, and other applications. A lot of talk, I know, yesterday around hydrogen, so I'm looking forward to this talk.
Yes, okay. Oops. All right. Well, ladies and gentlemen, thank you for having me today here. It's a pleasure to be finally talking live and not through a computer screen. And as Jean said, we are designing, building, and commercializing a waste-to-hydrogen system, a facility that, as you can see on this screen here, is designed to be extremely local, decentralized. Obviously, we will not install this system on Broadway, on Hollywood Boulevard, or on the Champs-Élysées, but still, the idea here is to offer a solution that would significantly reduce the logistics on the waste hauling, and of course, also, because hydrogen would be produced on site, solve, that other problem with hydrogen, which is logistics too. This is actually, so this is a drawing, an illustration, but it actually is taken from the very, very first system, a prototype, that was built in Germany some 20, 25 years ago, that was literally inside the city. So it's not totally science fiction here. What I will be talking about today is really a case, a business case, that we are working on right now for California. Why does this thing move by itself? Okay. We are, after about 20, 25 years development, this technology is finally ripe for commercialization. We are having a perfect storm now because of the pandemic that has triggered, and don't misunderstand me, I'm not saying that I'm happy about this, but the pandemic has triggered massive stimulus packages. We have the Biden administration, but it's also happening, the same thing in Europe. And a lot of these are centered, or at least are considering hydrogen development infrastructure. It helps a lot because 2 years ago, for example, when we started the company, we were talking to waste processing companies, waste haulers, and we were describing our wonderful technology that produces hydrogen, and usually the reaction was, well, yes, that's great, but what am I going to do with hydrogen? Well, this has significantly changed in the past 6 months, maybe, and so now we are really getting into commercialization, and so again, this case that I will be telling you about today is directly taken from a project we have here in California, where one of our clients will be taking waste and processing hydrogen to sell it to off-takers. So it's a system that will be installed on actually on a transfer station. And of course, because we are in California, as you all know, there is a need to divert waste from going into landfills. This is precisely what this system will be doing. In the first phase, it will be a 24-ton per day processing system. Of course, it will be producing renewable hydrogen that will be sold to there actually are two off-takers in competition that will be sold on long-term, the equivalent for hydrogen of power purchase agreements. I won't probably spend too much time on this slide. You all know what feedstock looks like. It's municipal solid waste. What's really important to realize here is that we are talking about a feedstock that is in majority, like above 80%, chemically organic. And chemically organic, it doesn't mean only biomass and biogenic matter like wood, paper, food, etc., but it's also plastics. Plastics are organic materials in the sense that they contain and they are made out of carbon and hydrogen. This is what we take. This is what we process. And like a lot of those solutions, we of course need to leave out the inert materials like glass, ceramic, and metals. But not only municipal solid waste, we also are developing solutions for captive industries that do generate their own waste streams. For example, we were talking with it's in Europe, but talking with a stakeholder in the food industry who has a mix of food waste and packaging, plastics, wood, etc. This is basically 100% chemical organic. This is a perfect feedstock for our solutions. And finally, unfortunately, I wasn't able to be here yesterday because I was in Oregon and in Washington State to visit a site over there. We were having masks, not because of the pandemic, but because of the smoke from the wildfires. And there are plenty of communities up there that are in a, I would say, dire situation because the lumber industry and the forestry has been significantly impacted by competition. And what we offer in this kind of situations is a solution that would be installed in small communities, process the waste, possibly process waste that comes from outside this community, and also help generating enough economic activity so that a very, very important fraction of forestry management, which is taking out the waste of trees cutting from the forest and bring it back, can be paid for. It means being able to manage forests, and it means being able to, at least to some extent, prevent wildfires. So, small systems. Small systems means that they are decentralized, and typically what we are looking at is deploying our systems in transfer stations, recycling yards, in those places where, again, there will be minimal logistics on the waste. And of course, the good news is in lots of cases, those sites are also very close to transportation nodes, highways, interchanges, etc., etc. So this is also good luck. This is also quite convenient for hydrogen fueling stations implementation. I should probably have been going more into detail about the technology. I'm happy to discuss this more in detail maybe after this presentation. You'll have my email address and contact information anyway. But basically what we do is, it is a thermochemical conversion. Thermochemical conversion, I use that word not to say gasification, because I know that the waste industry is not a big fan of gasification. There has been significant challenges with processing municipal solid waste using gasifiers. What I would like to emphasize is the fact that this technology has 25 years development, that from the beginning, from day one, has been specifically targeting processing waste and producing hydrogen. So we have had failures, we have had issues, but throughout those 25 years and five actually, different prototypes, we believe that we now have a system that is reliable, that will, as we all say, this is what we're looking for. It's the Saint Graal, something that works, that does the job. It's a process that is self-sustainable. I like to say that we use the carbon that is contained in the feedstock to extract the hydrogen that is contained in that feedstock. It requires electricity, which is the energy in terms of electricity that is needed for the system is really for motors, electronics, compressors, etc. So it's about 1/4 of the energy value that is extracted, or that is extracted as hydrogen. And we have a flue gas, and I will talk about this in a few minutes. We have a flue gas that is clean enough to be released in the atmosphere, but that can also potentially be sequestered, and this is something that is extremely interesting. Oh, all right. I was talking about biomass because we have sometimes we have some naysayers who say, oh, well, you have waste, you're using waste. You will not have enough to cover the needs for hydrogen. Well, you also probably know about this report from the US Department of Energy. It was released in 2017, called the Billion-Ton Report. It says that about 1 billion ton of biomass, and that includes waste, is potentially available in the US for harvesting. So a lot of this biomass is already used for energy crops to make ethanol, to make biofuels, etc. And I'm certainly not saying that we want to grab all this biomass to make hydrogen, but to keep things in perspective, it's important to realize that 1 billion ton biomass is about 50 million tons hydrogen, and those 50 million tons of hydrogen are keeping the tank-to-wheel efficiency in perspective, are equivalent to about 90% of the gasoline that is being consumed in the US today. So it's a significant potential source. Again, we will not use all of it, but it's not just some incidental process. So there is pathway, there are opportunities for significant large-scale development. You'll ask me how much this system costs. I will not tell you what the capex is. I'm happy to do that privately. But the calculation we are making, and this is in California, so there is this wonderful scheme called the Low Carbon Fuel Standard, LCFS, which is probably one of the most advantageous systems in the world. But typically applying LCFS credits, we need to keep in mind that the operators, and one thing is important, we are not interested in being operators. We do not operate systems. We sell the systems to operators who will make plenty of money processing waste, therefore generating the revenue that they, in most cases, are already generating by taking this waste from the waste generators, but also selling hydrogen and getting some LCFS credit. So with all that, we typically have a solution that considering opportunities to have the system under a lease contract can be an operation that is cash positive. Maybe not 1 year, I'm probably being a little too aggressive, but definitely after 2 years operation. And even without that, with a usual 30% equity and 70% debt, we do see our systems paying for themselves in about 5 to 6 years. But what's really important also is that it gives an opportunity to waste haulers, and specifically to waste haulers, to generate another activity and not simply be a pass-through, taking waste from one place, being paid for it, and then having to pay to send that waste to a landfill or to incinerators if it's not in California. So 24 tons per day, that's what I was mentioning earlier. It really is key to us because and I may be wrong because it's a figure I'm taking from Europe, so it might be slightly different here, but typically what we see that 24 tons per day of waste would be roughly the equivalent of what a population of 10 to 15,000 people is generating. And so it's a rather, well, small community or a small town. Out of those 24 tons, dry basis, we extract typically 1.5 ton hydrogen. If the plastic content is higher, we may go up to 2 tons. And interestingly, this is exactly what is needed for a fueling station. The average gasoline stand in the US today is servicing between 200 and 300 vehicles per day. This is what we have here. So we have a solution that is standardized, that comes as a module, that can be, by the way, the footprint for a 24-ton per day system, and I'm talking only about the system, not about the waste processing, the upstream processing, but the system itself has a footprint that's about 90 feet by 90 feet. And so with this, we can produce locally. We're really talking about circular economy here. We produce the hydrogen that is needed for a filling station. And you'll tell me there are not so many filling stations in this country. There are, at today's count, I think there are about 50. But, there are 110,000 gasoline stands. So I'm not saying that we will have 100,000 hydrogen filling stations even in 20 or 30 years from now, but there definitely is opportunities. There are opportunities to develop those systems, because wherever there is human activity, there is waste. We all know that there are several issues, environmental, financial, legal, with landfills and incineration. So the industry needs to find alternative ways to process that waste. And we believe that we're not the only one, and that's good news, because we would be too busy, and I'm a lazy person. But there definitely is an opportunity here to develop a system that, again, is standardized and that can be installed wherever there is a need for processing waste and producing hydrogen. I already covered most of it. Really the key for an operator is to be able, and it's even compared with other, for example, with green hydrogen production systems that are based on using electrolysis powered by renewable electricity. In that case, usually the bigger the better, but the bigger the better means that there will be a need to literally move this hydrogen from point A to point B, and there is a significant cost on that. Obviously, there are also a lot of environmental upsides. Being able to process the waste, not sending it to landfills or incinerators, but directly at the first transfer station, means less logistics, means less traffic, less roads damaged, less trucks, less emissions. And also, what is really, really important here, and this is what I wanted to talk about when I was talking about releasing the flue gas in the atmosphere. Obviously, our systems release CO2. That CO2 is short cycle. It is biogenic for most of it, at least about 80%. But so the carbon intensity of our systems is, in any case, is obviously much, much, much lower than fossil fuels. But we can also couple our systems, and this is something that is totally different from biofuels, because biofuels are used in every car, and you cannot connect a CO2 sequestration solution to each and every tailpipe that is using biofuels. Here, this CO2 emission is concentrated on one site, and this is on this site that we can connect our solution to a sequestration device or system that will literally do what is badly, badly needed, which is carbon negativity. We are all working today towards reaching zero emission. Zero emission is great, but we have, and there was a report about that, I think it was last week or the week before, we have already confirmed 1.5 degree temperature increase average. It means, well, we are on our way to 500 ppm CO2 in the atmosphere. So we, of course, need to stop emitting CO2, but even if we do that, we are already on the path of significant global warming. So this is, for example, well, and I'm not inventing anything here. This chart you can see here comes from the California Energy Commission, and what it says, it's very clear. This green part here is what is needed not only to curb emissions down, but to literally suck CO2 out of the atmosphere, take it out and bring it back where it belongs, underground. And this is what our systems can do, little by little, because 24 tons of waste is roughly 24 tons, a little more, of CO2, but that's per day. And this is, again, something that can also be done in a decentralized manner, because wherever there is human activity, you can see this on this map here. Those are, in blue, you can see the potential sequestration sites that are with saline aquifers. And so what we propose here is a solution where CO2, again, coming from biogenic feedstock, therefore CO2 that was not in the atmosphere 300 million years ago, but that was in the atmosphere maybe 2 years ago, 10 years ago, sending that CO2 back underground. I think that's about it. I'm happy to take questions.
Can you repeat the footprint for the system?
The footprint is about 90 feet by 90 feet, 30 meters by 30 meters, for a 24-ton per day system.
24. And you mentioned that your system can accept waste that is variable in composition, any type of feedstock, correct?
Absolutely. It actually is one of the keys and one of the big issues with conventional gasifiers. They do need a very, very controlled, stable quality for the feedstock. Otherwise, variations in the feedstock quality directly have an impact on the process temperature, and process temperature is very, very important for the system to be efficient and to keep working. The way our system is designed is that we use indirect heating for the pyrolysis vessels, and this indirect heating, because it is fed by the byproduct of all the reactions, actually have some sort of a self-stabilizing loop, which means that when there is variation in quality for the feedstock, it directly has an impact on the quality of the fuel we use for the feedstock. It might not be very clear the way I'm explaining it. It's usually better when I have the diagram showing the process. And again, I'm happy to give that explanation in detail. But yeah, our system is significantly more flexible to feedstock quality variations, which makes it interesting for the waste processing industry.
So I understand that you said that you would like to discuss that separately, but just if you have time to answer these questions, in terms of, from what you just said now, there's pyrolysis stage, and then I'm assuming that you got some kind of water-gas shift reactions happening as well, and catalytic process going on?
It's not some kind, it is water gas shift
It is,
reaction.
okay.
plus steam methane reforming.
Steam.
Because, yes.
So it is a conventional in many nature. It is a conventional process.
Well, the reactions are conventional. The way the reactions are maintained and the way the thermal energy is brought to the gasifier are totally not conventional.
Okay, so this technology, I mean, the conventional stuff has been tried over and over again, and the issues and with waste is that the catalysts pretty much die because of the contaminants in the feedstock.
Mm-hmm.
How were you able to overcome this challenge? Is that something you can share with us?
Oh yes, well, I really should have brought the diagram for our process, but we're no magicians. So obviously, when chlorine or sulfur or mercury or you name it get into the system, we have to take them out. Whatever organic contaminant is generated or circulates into the system, it is being scrubbed and taken out when we clean the syngas before we separate hydrogen. To make a very long story short, we have a first phase where we literally do the gasification, and we do that at about 700 degrees C, so high enough to make sure that we will not have tar. Then this syngas is sent to a second phase, which is basically reforming. So we raise temperature to about 1,000 degrees C, and there we push hydrogen content to typically above 50%. We have a hydrogen content in our syngas that is between 50 and 55%. Then that syngas is sent to a separator to extract hydrogen, and because we need to separate this hydrogen, we typically use a PSA for that, and we have to remove contaminants, otherwise we would kill the PSA. So we do have a gas cleaning phase in our process, and this is where we take out the, chlorine, sulfur, etc., whatever. And then the other part, like heavy metals and things like this, I was telling you that we use the byproduct of the reactions to generate the thermal energy for the process. The main energy source for us is the solid fraction of the carbon. In other words, in the first pyrolysis or gasification phase in our system, we typically extract 80% of the original mass, dry mass, as a gas, and we have 15, 20, 25% that goes out as char. We use that char and we burn it. And typically, the heavy metals as well as the mineral contaminants are recovered at that phase when we burn the char and we get the ash.
You're actually burning the char as part of the process?
Yes, sir.
To provide heat for the pyrolysis?
Exactly.
I see. So what are the final byproducts out of 24 tons per day? What do you have that needs to be taken away?
So out of 24 tons, again, dry basis, we would extract, like I said, about 1.5 ton hydrogen. Ash, so we have a solid byproduct, which is the ash resulting from the combustion of the solid fractions. That, when it's pure biomass, we typically are at 2-3%. In municipal solid waste, we would be more in the range of, I don't know, 5 to 10. And then the rest of it, so we have the contaminants that go out usually as a wastewater stream, very minimal, but an existing wastewater stream. And then most of the mass goes out as a flue gas.
Is there a facility like this running right now?
So we do have a system that is running. Unfortunately, it's in Tokyo, Japan, so it's a bit difficult to fly there at this point. But we are, as I speak, we are smoothly and nicely producing hydrogen out of sewage sludge in that system, and we are building another system that is intended to be a demonstrator that we will deploy here in California around November. But we already have more than 10,000 hours operation on the previous versions. Like I said in the beginning, I will not try to make you believe that the first prototype worked perfect on the first day we ran it. That does not exist. But still, we have been able, throughout those 4 generations development, we have been able to address, we think, again, we need to be confident but not crazy. We have been able, we think, to address most of the issues, at least all the issues that have been identified in conventional gasifiers. And as of today, when we run the current system, we don't see any problem.
Okay, to come off what he was saying also regarding feedstock, if you had a cleaner feedstock, not just the waste coming in,
yes,
maybe from a larger system, would that simplify and help your system? Let's say feedstock that was reduced in contaminants already. I'm thinking about, to be honest, the RDF.
Oh yes.
That kind of thing. Have a lot of carbons, a lot of stuff you can use, less contaminants.
Absolutely, absolutely. For example, we were talking to a so-called recycling facility in California. Unfortunately, they went out of business. I'm not really surprised, but anyway. And this recycling facility had a mix of about, I think it was 35% plastics that were the rejects from the recycling sorting processes, and the rest of it was paper. This is perfect. This is perfect. But again, I will not try to make you believe things that are not. Our systems, because we are just getting into commercialization, our solutions are still slightly on the expensive side. And so our operators are better off using each and every cent of the tipping fee that they are getting to make the system financially exciting for them. So yes, to directly answer your question, we have a project that we have actually, this week we have contracted it, and we'll go public on it probably around October with the details, names, etc. It's a system, it's not in the US, it's in the Caribbean. And the company who's our client, they literally take municipal solid waste from the city. They process it, and what they process it into what we would call RDF. They don't really need to pelletize it, so it really is a matter of sorting and shredding and having the right particle size. We typically have to like to have between, I would say, around half an inch particle size. So they process their waste into this. It adds to them a cost. I don't think I'm giving out a state secret here, but I think their cost for this processing is approximately $30 per ton. And then they give us this. And to give you an idea, what we would be able to extract about 1.5 ton hydrogen out of 24 tons municipal solid waste, the unsorted kind, of course, assuming metal, glass, etc. is taken out. Out of this RDF, we extract almost 2 tons. So the hydrogen yield is much better. Of course, there is a processing cost upstream, but the hydrogen yield is much better. And for at least 5 or 10 years from now, considering the price at which operators can sell hydrogen, it definitely is worth it.
Thank you.
Thank you.
Do we have any more questions?
All right, thank you,
Thank you.
JL. All right, David, you want to bring me up? Thank you. All right, so I wanted to just kind of share with you, just take a few minutes and show you this potential feedstock that could go for a lot of these projects, because I think it offers a lot of opportunity. What we're really talking about is what's known as agricultural film mulch. So if you've ever seen a strawberry field or a tomato field, it is an LDPE film that's used in the growing of that material. At the end of the growing season, just depending on where you are in Florida, they'll typically do 2 plantings on tomatoes and 1 planting on strawberries. There's roughly 40,000 tons of this material generated annually in Florida. Here in California, there's right at about 120,000 tons annually. So there's ample supply of the material. And I've been working on this issue since 1999, trying to figure out why this is not really sustainably recycled year in and year out. And I'll share with you some of the lessons learned the hard way from my perspective. I've done projects where we've collected it out of the fields. How do you get to it, and how do you transport? What's the logistics of it? So this particular grant that we did, we got a tobacco baler and put it on the back of a tractor. And as the film is pulled out of the field, it's typically pulled by hand. We then baled it, downstroke vertical baler here. And what you think is a clean bale of film weighs roughly around 1,200 to 1,500 pounds, is very, very far from it. And it's hard to get a handle on it, but I'll share with you some of the examples of what we've learned. In the state of Florida, we've had 3 different recyclers try to address this issue. Every one of them has gone out of business. And it has to deal with the amount of soil contamination related to the film. So we've got some very large stockpiles of plastics in Florida, both in situations where there were at former recycling facilities, or they might be out in the woods somewhere in the back 40 of a property. There are some extremely large piles of materials. It's typically, if you try to handle it when it's in this situation, it's almost like trying to move spaghetti out of a pot. It's really problematic to deal with. This is the option in Florida of how it's typically addressed. It's burnt in the field at the end of the growing season. Let me say that again. It is burnt in the field at the end of the growing season. It's hard to imagine that in this day and age that would be allowed, but it is. So what is typically done is it's piled up in these little piles and torched, and you can see this. This is in the field where they're growing the next set of tomatoes, right? So I'm trying to get some researchers involved in this to try to look at, what is the negative impact on the soils related to burning, petroleum product, and what's the uptake on the plants. Once it's burned, it's then typically just plowed right back into the soils. I wanted to get an understanding of the soil contamination rate, because I hear certain recyclers say, oh, well, it's 40%, it's 50% soil. No, it's not. In Florida, I can assure you, and you'll see from this particular trial I did, it's over 70% soil. I ran a trial with a cement plant where we collected 3,000 tons of mulch film out of the field and sent it to them. It's got a great BTU value, right? LDPE, this film, BTU value was around 19,000 if it's clean film, right? And got this one particular cement plant, 3,000 tons of material. After the first 1,000 tons, they processed. They said, Gene, thanks, but no thanks. We can't deal with this. We're spending $16,000 a week in blade replacements on our primary and secondary shredders. So the way their particular plant works, they've got a primary shredder, which shreds down to about 6" minus. And then it goes into a series of belts with belt magnets, and then from there it goes into a secondary shredder, which shreds down to 2" minus, and then they blow that into the Kelshiner pneumatically. Way too much wear and tear on their shredder blades, so they said, let's stop. So this is where I wanted to get a better understanding of what we were dealing with. In this particular, let me go back to here, it's kind of hard to see, but there's roughly a 16-ounce sample of film that we had shredded, took it out. I then washed it, and out of that 16 ounces, I got 4 ounces of clean film, 8 ounces, almost 8.5 ounces of soil. It's just really hard to believe how much soil is there. And when you look at it, it doesn't look like it. So then I got to thinking, and this is where I need help from everybody that's in this room and is listening virtually and will see this down the road. How do you solve this problem? How do you take something that is so problematic to recycle and put it back into where we can recover it as a feedstock for some process? Whether go into a pyrolysis system, or whether it goes into a cement kiln, or what have you. Even traditional recycling, we've got to figure out how to deal with the soil level. What I decided to do was to run a trial. I was thinking somebody's got to be able to address that much wear and tear on dealing with hard to recycle materials. Sand is basically. And I thought, well, wait a minute, now C&D industry. C&D industry has shredders. They've got tub grinders that grind trunks of trees that have got sand associated with it. So I decided to reach out. This was one particular company. This is a Tana unit, and it's a mobile shredder. And I thought, well, why don't we shred, and then from there, let's run it into a trauma screen. Let's see if I can't reduce some of the soil level that way. So Ran that trial, it was very successful. We were dropping soil levels down to about 40%, but it's still not good enough because you still have a level. You've got shreds of material, 2-inch minus to 4-inch minus materials, but you still have that soil content that sticks to that film. I then ran another trial. This is a mezzo shredder, and I tried a different shaker screen, if you will. This is an eco screen. And this worked great too. So, the thought process is maybe to do a series of types of equipment. The mezzo shredder and the Tana shredder, there are about 6 different shredding companies out on the marketplace right now that does that type of shredders. It will process roughly 20 tons an hour. So, you can get the volume you need to make a project successful. You just got to figure out how, 70% of that 20 tons an hour is soil. So what are you going to do with the soil? How do you extract it? So I envision probably a series of lines like this where you shred and then perhaps go into a wash line. If you can try to alleviate that wash line so you're not dealing with effluent and large volumes of water, then that would be the ultimate way to go. I did have one company a couple of years ago, a company called Broadview Group, and they ran a trial. They're a company that does recycling of carpet. And so they've got a process where they shred, and they've got a dry clean process where they separate out calcium carbonate and other materials that's in the carpet, and then they take the nylon or the polypropylene or whatever it is and go for recycling for that. I had them run a trial, and they were pretty successful in reducing the soil coming out of this, if you all want to see this, and then they actually took it a step further and pelletized the LDPE. So I think there's an opportunity on that realm. I think that if somebody else can do it without having to pelletize and go straight into a pyrolysis unit or some type of recycling facility, I think this, like I said, I think there's a lot of great opportunity here that somebody needs to look at, because it's not just ag film mulch that this could be applied to. You've got silage cover. You've got grain bags that are used in the Midwest and actually starting to show up in the Southeast. And so there's some pretty big volumes of agricultural plastics that have the nexus to the waste conversion industry. Just wanted to share those thoughts with you. And I'll take any questions in case anybody has them. Yes, sir, Glenn.
If we can get it down small enough in size, and even with some of the soil that might be left on little pieces, you were saying, Mr. Kindler, half-inch would be the best. I think you could take, 40 millimeters or maybe something like that too, maybe even a little bit larger. That would be a perfect feedstock.
Actually, it's interesting because the project that we constructed in the Caribbean, they have huge banana fields, and something I didn't know is that banana fields.
Hang on one second. We're not picking up. I didn't think about that.
When bananas grow, they are literally put into a bag, a polyethylene, film bag, to protect them, I guess, from scavengers or something. And one of the feedstocks we have in that project is 3,000 tons per year of that film. That probably is not as loaded as this one with soil and minerals, but and in that case, we do not really need to cut it down to half an inch because it is extremely thin. In the second prototype that we built, it was in Japan in the year 2000. I actually was responsible on site for the engineering and operation of this system, so I know it very well. And we were processing construction waste. And so construction waste in Japan, just like in many areas in this country, is mostly wood. And so we had wood chips or wood shards that were actually quite long. We were having maybe 2-3 inch long. But because it is thin, the thermal transfer between the heat carriers that we use and these particles is as good as if it were cut down to half an inch. So film, we can have much longer particles.
What size do you think would be?
What size?
What size? Let's say maximum size that.
I remember we had chips that were about this size. So what? It's
80 millimeters.
3, 4 inch. No, maybe yeah.
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 Yes. So the challenge looking at the film itself, if you look at it under photomicrograph, the sand particles, the dirt particles, et cetera, get embedded into that matte surface of the film. So the challenge is just not knocking it off or washing it off. It's embedded into it. So how do you decouple it?
That's a great question, Dan. You know, from the research, so I took some of that film, and I took it over to FSU through the chemistry lab, and we put it under a microscope to look at it. The film actually mulch film has an embossed pattern, and it's hard to see it with the naked eye. But if you can envision a screen an outside screen for a porch or whatever, you've got these little small patterns that are built into it. Those patterns do two things. It acts as a rigidity, so it gives the film strength. So when they stretch it over the mound and then tuck it under the ground, it doesn't rip. But what that pattern does is it almost acts like a suction cup. And it allows the small micro dust to accumulate on that film. So you're going to have that amount of dust particulate on the film, as well as what you're talking about is when you shred, when we went down to 2" minus, we were releasing steam because that film was starting to get hot. So you had the situation where the film was actually incorporating, basically making a sandwich, if you will, of soil, right? And so you've got to be able to deal with that. Whatever system that you're using, it's got to be able to deal with some level of soil and silica, and I don't know what the solution is to separate it out further.
Easy question. Can you just repeat what the mass generation of the film from the tomato?
40,000 tons in Florida, mulch film, and that's going to go up because we've got a lot of hemp industry starting in the state, and a lot of the hemp industry growers use, at least on the CBD side, cannabinoid sides, they're going to use mulch film, so that number is going to go up. In California, it's roughly 120,000 tons.
And is that the film itself or the film?
That's the film itself, right? So the film, in addition to the film on the recycling side, you've got roughly an acre of field will have roughly 250 pounds of mulch film. You then have about another 60 to 70 pounds of drip tape, right? So drip tape is what they use to blow water into the field, so that goes underneath the mulch film. Yes? Yeah, and when you bale that stuff up, that water is there, and the longer it sits in the field, when they're pulling it, just depend on when they pull it. They might pull it on a rainy day, so that film's going to have water content in it for sure. Yeah, absolutely.
So, Gene, have you talked to anybody about a thermal process where perhaps you can just process this film with the soil as is, dirty?
Well, yes, I have. I talked to Mike Hart about this, right? So he's got the fast ox, the gasification. I would think if they could take that, they could gasify it, and then what you're left is a slag that's going to come out with the soil content. So that might be an option.
Well,
the question is the expense.
Yeah, but so that's where the issue is, the economics.
Yeah.
And depending on the process, where this material is 40,000 tons spread over a large area, that's where the issue is. But if you can define the logistics behind it,
yeah,
where now the economics start to make sense. What is the size of the system, and what processes it is? I would think that a pyrolysis system would work better than a gasifier in this case, for a lot of reasons. and it depends on which pyrolysis system you would use and how would you pelletizing a film plastic like this is hard, especially you mentioned, the shredding is an issue, right? But there may be some kind of an optimal way where, there's a sweet spot. What is the particle size and what kind of densification process you would use to make that material compact enough? The sand might actually be a catalyst. It might help in a thermal process. So there may be, that's how I would think you should think about it, as opposed to shred, clean, and then process. Think about the process where the sand becomes a catalyst to do this, because you're gonna end up with char that's gonna be dirty, full of sand.
Right.
Which is fine, right? But and if that char is clean, this doesn't have any volatiles in it, then it doesn't have any harm to the soil. But again, there's a lot of ways to do things, but how much they cost, right? So it's important to know the 40,000 is where is it? I mean, if you have
In
to collect
Florida,
it from
it's in a relatively short area. It's in the center part of the state of Florida, located from roughly Orlando down to, if you know where Naples is, Collier County. It's in the center part of the state there. That's where the bulk of it, I would say 85% of the mulch film is generated there. In California, it's in the Salinas area. There are several different spots in California, so you're not going to have all of it because of the length of California. You're going to have different areas.
This needs a little bit of research up front, because I don't see a solution that's ready to go for this specific case.
No.
If you want to talk about it in detail, we may be able to collaborate with you on how to do some upfront analysis and see where this can go, right? Because it's a seasonal issue.
Yes.
So that's another factor.
Yep.
It has to be, it's not something that you can design and build where somebody's be making money from it all the time. So that's where the constraint is, right? Yep. So we'll be more than happy to help.
All right, thank you.
So real quickly, are there any, to assist in collecting the material, any producer laws or any legislation that one might be able to enact in Florida, California, wherever, to help get the producers of the material, the sellers of the material, to start collecting it back so that you have it in one location? And then, with regard to processing it, would the contaminants, as Gene laid out, would they impact your system, for example?
What we really don't like to have is chlorine.
Oh, okay, gotcha. That's true.
But chlorine comes out of PVC, but other plastic types actually do not have much chlorine content. We do see a lot in food waste, for example. Okay. We see chlorine, but it's not really directly related to this, but I remember in France a long time ago, well, we still have lots of incinerators there, and there were regulations about plastic bags that had to be made with a certain type of, it was not a bioplastic, but it was some plastic that when burnt does not generate the kind of contaminants that are generated normally. And so, to your point, it might be interesting to have a look at pushing some legislation to, or maybe talk to the producers of those films to have something that would not do any harm, or that would do minimal harm when being burnt on the field.
Yeah, Tom, to that point, there isn't any producer responsibility yet for the film. Here in California, they do have some legislation for carpet. And there's responsibility there where after, forever, how many cubic yards of carpet is sold, there's money that goes into a trust fund to help out on that. That could be helpful.
So we take a look at this on multiple levels. With regard to cost, who's going to pay it? Like polyethylene is the largest polymer produced in the world. It's the lowest cost polymer. So if you now legislate something that's 5 times as expensive, who's going to buy it? The other part to this is we talked about the composition and what goes into it. We have to really take a look at the contaminants. You talked about catalytic processes. How do you handle the phosphorus, the nitrogen, and the various other metals and materials that are in there that will kill catalysts very quickly?
I wouldn't do fuels in this case. I would look for something else, or maybe power or something like that.
Again, it comes down to economics. It comes down to economics. And as far as using this in a pyrolysis process, if you still have 10% soil in there, there's going to be so much char you overwhelm the process.
No, I mean, polyethylene needs very little char to start with, but what are you going to end up with? The sand that's contaminated with char. That's what you're going to end up with.
Then what do you do with the char? Then the char becomes a problem itself to deal with.
Char, if it is passive, just carbon.
It's not carbon. It's soil. It's sand. It's
Sand that's got enough char. It's got enough carbon. Carbon, if it is not volatile, doesn't have any volatile matter, is actually maybe it's not at the level of you can fill it with use it in for areas that can actually improve the soil.
Yeah, the
conditions.
40,000-foot level, it seems really easy. But once you get down to the 5-foot level, it's almost insurmountable.
Which is why the problem
No,
has existed for this long.
No,
you know?
that's why I said, this requires some research, okay? Just at this level, looking at it this way, the sand, it could be a catalyst for a thermal process. I wouldn't, polyethylene, by the way, has very little chlorine, comparison, it's not PVC. So, and it doesn't have, what other contaminants that can actually harm catalysts? I wouldn't do fuel cycle here anyways.
One of the options that we are looking at, and there is some folks that are actually starting to test it, is particularly possibly using this in asphalt. Right?
Yes.
They're starting to incorporate plastics in asphalt right now. And so this might be a particular case in that because it doesn't matter what the sand is, right?
Exactly.
It's going to go into asphalt.
Yeah, the sand, the carbon-based sand, this would be perfect for asphalt.
Yeah.
But how do you get the hydrocarbons out of that? That's the question. I think I would think the easiest way is to pyrolyze, get a pyrolysis gas out of it, send it to a boiler, make electric power. The issue is that, okay, you got 40,000 tons per year accumulator, right? You can't have, if it's a farmland that's big enough using power, why not? Maybe there's a way to do this. But like I said, somebody has to sit down with a clean sheet of paper and a pen and do these calculations, if it makes sense. But that's the fastest way I would think of. Yeah. Sand contaminated with soil, with carbon, even if it's not clean carbon, still has the volatiles, it can go to asphalt. Good idea, I would think.
Well, hopefully, after this is done and my ag plastic is done, I'll be able to report. Maybe somebody else will come up with some more ideas on this, because it's not going away, so not anytime soon. So hopefully we'll solve it.
If you can find somebody who would pay for some work, I can put some engineering resources for you, and we could do it.
Maybe we go after some funding to do that.
Sure.
All right, if there's no other questions, I want to thank everybody. We are going to go ahead and adjourn. Just keep in mind that I will be sending out, it'll be next week, because I've got this other conference to start here in 2 hours. I'll shoot everything, all the presentations to PDF, and get that out to everybody along with the video recordings. So thank you, everybody. Let me just mention that we've already started the process of talking about next year. Just depending on how things go, we may come back together and do this again here. So I'll keep everybody posted. Thank you.